Welcome to Free Learning Academy. Let's simplify multi-level queue scheduling. Have you ever noticed how your mouse keeps moving smoothly even when your system is busy doing something heavy in the background, like a full backup or a large file transfer? Or how an important system alert shows up instantly, even if you are in the middle of rendering a high resolution video? That is not happening by chance. The operating system is deliberately prioritizing certain tasks over others. It understands that some processes need immediate attention, while others can continue quietly without affecting your experience. This smart grouping and prioritization of tasks is what we call multi level queue scheduling. In earlier discussions on scheduling, we saw algorithms like round robin, priority scheduling, and SJF. Each of them had a specific way of deciding which process should run next. But here is the problem: real systems are not that simple. They do not run just one type of process. Instead, they handle a mix of interactive tasks, background jobs, system processes, and batch operations all at the same time. Using a single scheduling algorithm for all of them often leads to inefficiency. Multi level queue scheduling solves this by dividing processes into separate groups or queues based on their type and behavior. Think of it like a hospital. There is an emergency ward, an outpatient department, and a general waiting area. Patients are not treated in one single line. Instead, they are categorized based on urgency. Similarly, in multi-level queue scheduling, processes are placed into different queues depending on their priority or nature. Each queue can have its own scheduling algorithm and rules. Now let us understand how these queues are actually formed. Processes are usually divided based on characteristics such as whether they are interactive or batch, system level or user level, or CPU bound versus IO bound. For example, one queue might contain interactive processes like a text editor or a browser. Another queue might contain batch jobs like large file processing or backups. A third queue might be reserved for system level processes that are critical for the operating system. Once processes are assigned to a queue, they stay there. This is an important point. Unlike some advanced techniques that allow movement between queues, in multi-level queue scheduling, processes do not change their queue. The classification is fixed. This makes the system simpler, but it also introduces some limitations, which we will touch on later. Now comes the interesting part. Each queue is treated separately, and each can use a different scheduling algorithm. For instance, the interactive queue might use round robin so that users get quick responses. The batch queue might use FCFS since those jobs are not time sensitive. The system queue might use priority scheduling to ensure critical processes run immediately. But how does the CPU decide which queue to serve first? This is where scheduling between queues comes into play. There are two main approaches. One is fixed priority scheduling between queues. The other is time slicing between queues. In fixed priority scheduling, each queue is assigned a priority level. The CPU always selects processes from the highest priority queue first. Lower priority queues are only considered when higher priority queues are empty. For example, suppose we have three queues: system processes at the top, interactive processes in the middle, and batch processes at the bottom. If there are always system processes waiting, the CPU will keep executing them, and batch processes may never get a chance. This leads to starvation, something we already discussed earlier. Let us take a simple example to make this clearer. Imagine three queues. Q1 is for system processes with the highest priority. Q2 is for interactive processes. Q3 is for batch processes. Suppose Q1 always has at least one process. In that case, the CPU will continuously serve Q1 and the other queues will remain waiting. This is efficient for critical tasks but unfair for lower priority processes. To reduce this issue, the second approach is used, which is time slicing between queues. In this method, each queue is given a certain amount of CPU time. For example, the system queue might get 50% of CPU time, the interactive queue 30%, and the batch queue 20%. The CPU switches between queues based on this time allocation, ensuring that every queue gets some execution time. Let us visualize this with an example. Suppose the CPU cycle is divided into 100 milliseconds. The system queue runs for 50 milliseconds, the interactive queue for 30 milliseconds, and the batch queue for 20 milliseconds. Even if the system queue has many processes, it cannot take over the entire CPU. This ensures fairness while still maintaining priority differences. Now, let us bring everything together with a practical scenario. Imagine you are using your computer. You are typing a document, listening to music, and at the same time, your system is running a backup process in the background. The typing and music are interactive processes. The backup is a batch process. In a multi-level queue system, your typing and music will be placed in a higher priority queue, ensuring smooth user experience. The backup process will be placed in a lower priority queue, running only when higher priority tasks are not demanding the CPU. This explains why your system feels responsive even when heavy background tasks are running. The OS is intelligently separating processes and scheduling them based on their importance. However, multi-level queue scheduling is not perfect. One major limitation is the lack of flexibility. Since processes cannot move between queues, a process that was initially categorized as low priority will always remain there, even if its behavior changes. This can lead to inefficiencies. For example, a batch process that suddenly becomes interactive cannot shift to a higher priority queue. Another issue is starvation, especially in fixed priority scheduling between queues. Lower priority queues may suffer if higher priority queues are always active. This is why more advanced techniques like multi-level feedback queues were introduced later to overcome these problems. Despite its limitations, multi-level queue scheduling is very useful in systems where process types are clearly defined and predictable. It provides a structured way to handle different workloads and ensures that critical tasks get the attention they need without completely ignoring others. So, if you step back and look at the bigger picture, multi-level queue scheduling is about organization. Instead of treating all processes the same, it acknowledges that different tasks have different requirements. By grouping them into queues and applying suitable scheduling strategies, the operating system achieves a balance between performance, responsiveness, and fairness. And this idea of classifying and prioritizing work is something you will see again and again in operating systems, especially as we move toward more advanced scheduling techniques in the next topics. That is it for this video. See you in the next one.